Okay, Chapter 7 is arithmetic operations and circuits. So we're going to do math operations, but we're going to do it in binary, and we're going to see how that's implemented in circuits. So I will say that we can implement it in circuits, but we can implement it in software, which is probably more what you're used to thinking of. But ultimately, down inside your computer, it's being implemented in circuits again. So anyway, we'll start with addition first, adding two numbers together. This is somewhat obvious. It's just a truth table for adding two binary digits. So 0 plus 0 is, as you expect, the sum is 0, right? And then this column on the right, the C out, this is your carry bit. So we do lots of carries in binary. So 0 plus 1 is 1, as we expect, with no carry. 1 plus 0 is also 1, which we expect. I mean, just like in base 10, and no carry. But 1 plus 1 is what? 1 plus 1 is 1, 0. So let me get my markers here. 1 plus 1 is 1, 0. 1 plus 1 equals 1, 0 in binary, because after all, 1 plus 1 equals 2. And that's in base 10, and 1, 0 represents a 2. So what do you have? You have that the sum in the same place is a 0, and a carry bit is a 1. So I think I'll take that just a little bit further in the next example. Okay, first example we're going to do is 5 plus 2, which we know equals 7. So 5, and I'm going to do everything in 8 bits. So 5 would be 4, 5. That's the number 5. And 2 is a 1, 0, 0, 0. And we're going to keep everything as 8 bits because that's how it would probably be done in the real world. And so we just add these up. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1, and all these zeros add up, and so that equals 7, base 10, no problem. Next problem. Next problem is 18 plus 2. 18 plus 2, and that answer is 20 in base 10. So 18 is going to be 16 plus 2, so 16 would be there. So that's 1, 2, 4, 8, 16. So 116 plus 2 more. Oops, that's 18. Yeah, 18 plus 2, that makes 18. And 2 is a 1, 0. 0, 0, 1, 2, 3, 4, and once again I'm sticking to everything to be 8 bits. So we add this up. 0 plus 0 is 0, but 1 plus 1 is 1, 0. So I have to carry the 1 there. And so I have 1, 0, and then bring that down because now the carry 1 plus 0 is 1. And that's our answer, and that's the 16. And that's a 4, so it does equal 20. Check. Okay. Next problem. So magically appeared is we're going to do 147 plus 75, which will be 222. So convert everything to binary. I just want to check that this is truly 147. So that's a 1, 2, 4, 8, a 16, 32, 64, and 128. So 128 plus 16 plus 2 plus 1, that's 14, 15, 16, 17. So that first number in base 2 truly is 147. Let's check if this bottom one is a 75. I have a 2, a 1, an 8. 2, a 1, an 8, and a 64. So that's 12, 13, 14, 15. Check. Okay, so that binary conversion is truly correct. So now let's add these up. So remove some of this excess stuff here. So 1 plus 1 is 1, 0. 1, 0. So I have to carry a 1. Now 1 plus 1 plus 1 is 3, right? And 3 is 1, 1. So 1, 1, there's my carry, and there's my 1. So that's 1, 1. And then I bring it down. That's a 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. And 1, 1. That's the answer. Let's see what that is. That's in the 1s, 2s, 4s, 8, 16, 32th place, 64, and 128. So I have a 128, a 64, a 16, an 8, a 4, and a 2, and it's 10. So these should add up. That's 20, 32. So 6, 7, 10, 11, 12, 222. Yes, it does add up to 222. But the trick to note here that 1 plus 1 plus 1, right here, 1 plus 1 plus 1 is 1, 0, is 1, 1, or 3. So that's how you do the carry. Okay, next problem. 31 plus 7. So 31 is that's 31. Yes, 1, 2, 3. So 1, 2, 4, 8, and a 16. That would make 31. And 7 is 1, 1, 1. And we'll keep everything being 8 bits. So let's add this up. 1 plus 1 is 1, 0. There it is, 1 plus 0. 1 plus 1 plus 1 is 3, which is 1, 1. So I have to put 1, 1. 1 plus 1 plus 1 is again 3. So I put 1, 1. And then 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. And then 1 plus 0 again is 1, 0, 0. So that's the answer. That's a 2, a 4, no 8, no 16, and there's a 32. So my answer is 32 plus 4 plus 2 is 38. And yes, indeed, the answer is 38. Okay, so that's addition. It can get messier than that, but one thing that I want to point out, especially going back one slide here for a moment, is that we have to use this carry bit, which is a cout on integrated circuits. And the sum is adding the two binary digits together, and then there's a carry. And so you can imagine that these kind of things stack up. That you have from A0 plus B0, you have a sum plus a carry, and the carry goes over here to the next digit. And then you have the carry in, and then the sum of these three things together makes a new sum, and then there's a carry out, and the carry out goes to the carry in of the next most significant digit. So these devices stack up on a single bit, but with the carry ins and the carry outs. So next let's look at subtraction, and we're actually going to look at subtraction two ways. So let's just look at what happens in subtraction. Let's say I have 2 minus 1. So what you have to do is borrow. So I'm borrowing a 1 and moving it over there. Now I have 2 minus 1 in the least significant digit place, and 2 minus 1 is 1, and then we still have 0 minus 0 right there. So we had to borrow So here's the truth table. Of course, 0 minus 0 is 0, and you didn't borrow anything. 0 minus 1 is 1, but you have to have a borrow, and we'll go over that in a moment to show how you get a negative number. 1 minus 0 is 1, no borrow, and 1 minus 1 is 0, no borrow. So this case of having a borrow is the one that's going to be interesting. Let's do another example. We are going to do, let me get rid of this one right here real quick. We are going to do 4 minus 1. 4 minus 1, which you know is 3. And a 4 is 1, 0, 0, minus 1. So it's minus 1 right there. So how are we going to do this? So this requires a borrow twice. And there's two different ways people look at this. Sometimes you can say, I'm making this a 0 and moving the 1. I'm borrowing 1. So that's a 1, 0. But what's 1, 0? 1, 0 is really the number 2 in decimal. And I'm not there yet. I need to borrow to the least significant place. So I can cancel this one out and make this one a 1. And then carry over here. It's 1, 0, which is really a 2. So 2 minus 1 is 1. 1 minus 0 is 1, and 0 minus 0 is 0. So here is our answer in base 2, which is the number 3. So it checks. So that just shows a little bit more about borrowing. Let me do another example to make that sure that's clear. 1, 0, 0, 0, 0, minus 1, 0. So this number is 1, 2, 4, 8. This is number 16 minus 2, and my answer should be 14. So one more. So 0 minus 0 is 0, no problem. Here's where we start having the problem, the next significant digit. I can't borrow from 0. I can't borrow from the next 0. I have to borrow all the way from the place that there's a 1. So I cancel that out and make a 0. That makes this next one be 1, 0, which is a 2. 1, 0 is a 2. Oops, borrow 1 from that. Make this one now a 1, 0, or a 2. Borrow 1 from that. Make this one a 1, 0, which is really a 2. So 2 minus 1 is 1. 1 minus 0 is 1. 1 minus 0 is 1. And 0, 0 is right there. So did I get the right answer? This is 2, 4, and 8. That's 12, 13, 14. Yes, indeed, I got the right answer. So then we can make a truth table with borrow ins and borrow outs bits, which is similar to our carry in and carry out bits that we had for addition. And it's a little probably confusing to look at the truth table and figure it out. So fortunately, for subtracting binary numbers, we have a process that's much easier than doing this called 2's complement. And that's how computers will do it algorithmically. But first, we should make sure that we're able to do subtraction, binary subtraction. Just if I give you two numbers, you can do the binary subtraction, you can do the binary addition, the multiplication, and the division. But then I'm going to show you how to do the 2 complements for subtraction, because subtraction otherwise doesn't lend itself very well to doing it in an algorithm. So let's try a few more subtractions for practice, and then we'll move on to multiplication. So I'm going to jump right to the toughest one, example, because I think that lets you see the pattern the best. So here's 192 minus 3, which the answer should be 189 in base 10. So here's 192, here's 3. I'm going to subtract the 2. But right off, I cannot subtract 1 from 0, so I have to start doing my borrowing. So I'm going to move to the left until I find the first place to borrow from. It's right here. I'll make that a 0. I'll make this guy a 2, but then that doesn't solve my problem. So I'm going to borrow it from it and make it a 1. Make this guy a 2, but I'm going to borrow from it and make it a 1. Borrow 1 over, so that makes this guy a 2 or 1, 0. So, but I'm still not there yet. I'm going to borrow from it, move a 1 over to here, put it over there. That's 2. It's now a 2, but I'm going to borrow from it again, move a 1 over to here. That's 2. Nope, but I'm going to borrow from it again and take a 1 and move it right over there. So now that's 2 in decimal. So 2 minus 1 is 1. 1 minus 1 is 0. That's a 1, 1, 1, 1, 0, 1. And that's the answer. And that should come out to be 189 in base 10. And I do believe it does. Let's try one more just for the fun of it. 154 minus 54. That answer should be 100, not 100, which is a 4. So convert that to binary. Minus 0, 0, 1, 1. Keeping everything at 8 bits. So 0 minus 0 is 0. 1 minus 1 is 0. I need to borrow, so I'll make that a 0, make that a 2, or in other words, a 2. 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 1 is 1. I have another problem. I got to borrow again because I can't do 0 minus 1. So let's go over here and make that a 0. Which makes this guy a 1, 0, which is 2. But I'm going to borrow from it again and make this one a 1, 0, which is 2. 2 minus 1 is 1. 1 minus 0 is 1. And 0 minus 0 is 0. So that comes out to be 1, 2, 4, 8, 16, 32, 64. Let's add those up. 64, 32, 16, and 4, 10. Oh! 10 and 6 is 16. Whoops, do I have a mistake? I think I have a mistake. Okay, let's see where I made a mistake. Probably in my original binary conversions. 1, 2, 4, 8, 16, 32, 64. And 1001. So I need to check that I set that up right, because I do get, 1 minus 1 is 0. There's my mistake right there. So I don't have a 16. So I have a 64, a 32, and a 4. So that's, yes, that does add up to be a 100 in base 10. Yep, there is my mistake. 1 minus 1 is 0. Okay. Multiplication of binary numbers is simple in that you're always multiplying ones and zeros, but then you'll have all of these numbers in between that you have to add up. So it's performed mechanically very much similar to how you do it in the decimal number system, except that sometimes it's a little tricky adding these numbers up in the end. So I'm going to do an example where you watch me do it, because I think that's the easiest to see rather than looking at the answer right there. So let me do that. And we will do an example where you can watch me do it, and then it's kind of more interesting. So first one, let's just to get the idea. 5 times 3 is 15, right? So 5, keeping everything 8-bit. 5 is 4 and 1, so that's a 5. And 3 is 1, 1. And we want to multiply these two together. So it's pretty much the same as how you've done long multiplication in your past. So keeping all of the columns well aligned. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. And then I have 1 times, and each one of these cases is a 0, so that will be zeros. The same thing happens with the next most significant bit. I'm multiplying 1 times this top number, which is called the multiplicand, right? Oh, by the way, multiplicand. And this is the multiplier. So my multiplier is 1 again, which I got a times it times this whole multiplicand, which, I mean, it's either a 1 or a 0, so these are 1s. 1 times something. 1, it just repeats, right? Looks like that now. And the rest are all zeros. The multipliers are all zeros. So I could technically put all of these zeros out here in the answer, but putting zeros in front of anything doesn't change anything. So now we add these up. 1, 1, 1, 1. And that is definitely 15. And then I don't care how many leading zeros I put in here. It doesn't change the answer. The answer is still 15. So that's first problem. Let's get them progressively hard. Okay, so let's show you an example. How fun this is. I actually think this is kind of fun. I'm going to do 15 times 15. So that is 225, and base 10 should be my answer. So 15 is, that's 15 times 15. Now when you do this problem, it's going to be really important to keep these columns aligned. And it's hard for me on my little drawing pad sometimes to keep my columns aligned. And if I don't, I'm going to make a mistake. So here we go. So this is the multiplicand right here, just to get our terminology straight. And this is the multiplier. So very similar, same process as how we do for base 10. I'm going to take my first multiplier is 1 and multiply it times the multiplicand. So pretty straightforward. 1, 1, 1, 1, 0, 0, 0, 0. Take the next multiplier, next digit, the multiplier is 1, and do the same thing. So 1 times the multiplicand. So 1, 1, 1, 1, 0, 0, 0, 0. And again, third bit, same thing. 1, 1, 1, 1, 0, 0, 0, 0. And the fourth multiplier is again a 1. Put it there. 1, 1, 1, 1, 0, 0, 0, 0. Now we have to add these up. So this is where the fun comes in. So I'm going to change colors a little bit so it highlights better. So first column, keeping in mind the columns of information, the first column I added up. 1 plus a bunch of zeros is a 1. No problem. Second column, 1 plus 1 is 2, which is a 1, 0. So I'm going to carry a 1 and 0. So that's 1, 0, because 1 and 1 is 2, which is 1, 0. Okay, fun now. Here is my third column, and there are 4 1s in it. So 1, 2, 3, 4 1s in it. So that's 4. So 4 in base 10 is 1, 0, 0. So this is the number I have to put down. So what I do is do this. 1, 0, 0. So that's how I account for the fact that it takes me 3 weighted placeholders to express that sum. So see my 1, 0, and then 0. Here's my next column of numbers. There are 4 ones in it. So that's a 4 again, which is 1, 0, 0. So we're going to go over here and write 1, 0, 0 again. 1, 0, and 0. Okay. So now I'm going to go to my next column of ones right here, and there are 1, 2, 3, 4 ones in it. That's a 1, 0, 0 again. So 1, 0, and 0. Next column of information, 1, 1, 1. That's 3. There are 3 ones there. That's a 1, 1. So 1, 1. Sorry, I'm running out of space. I should have given more space here. Next column of information is 1, 1, 1. That's the number 3, which is a 1, 1. So I will say 1, 1. Okay, next column of information, column of numbers only has 1, 1 in it. So beautiful, 1, 1, and the rest is zeros here. So is that the correct answer? I have a 1, a 2, 4, 8, 16, a 32, a 64, and a 128. And I add that up to check. 128, 64, 32, and 1. 12, 13, 14, 15, 9, 10, 11, 12, 225. Yes, it does check. So here's my answer in base 2. So the main trick is seeing how you carry over the numbers. I hope you could see that it wasn't too small in your YouTube. I almost want to do that one more time so that you can see it. Maybe I should. One more example, somewhat similar, just to make sure that you can see it. I am going to do 15 times 30. And so that answer should be, and this one's not in your book, 450. Oh boy, bigger than 8 bits, because it's past 255. But okay, 15 is 0, 0, 0, 0, 1, 1, 1, 1, and 30 is 1 less than 31, so 30 is going to be 1, 1, 1, 1, 0. 1, 2, 3. Okay. It doesn't matter whether I say 15 times 30 or 30 times 15. Really doesn't matter, but I'm just going to write it big enough for you to see. So 4, 1, 1, 1, 1, and 0, 0, 0, 1, 1, 1, 1, 0. This is what we want to multiply, but the main thing is I'm going to leave some space right here so that you can see me do my carry bits better, because I think that part might not have shown up very well last time. So first case, my multiplier is a 0, so I can just write down a 0. Oops, I said I was going to give more space. My multiplier is a 0, so I can just write down a 0, right? No problem. Next case, my multiplier is a 1. 1 times the multiplicand, so 1, 1, 1, 1, 0, 0, 0, 0. And I've got to repeat that 4 times because there's 4 places where the multiplier is a 1. 1, 1, 1, 1, 0, 0, 0, 0. Again. And one more time. Okay, this is the thing that I have to add up, only this time I left a little space, hopefully, so you can see when I add in the carry bits better. So let's do it. Just bring down the 0 right here, no problem. Just bring down the 1 in that column, no problem. Okay, 1 plus 1 is 2. That's 1, 0. Here we go. 1, 0. Next column, there are 4 ones in that column, so that's 1, 0, 0. So this is what I have to do. I have to say 1, 0, 0. That's how I add it up. Next column, there are 4 ones in it again. That's 1, 0. That adds up to 4, which is a 1, 0, 0. So here I go. 1, 0, 0. Next column, there are 1, 2, 3, 4 ones in it. So that adds up to 4. So one more time. 1, 0, 0. Okay, next column, there are 1, 2, 3 ones in it. That's 1, 1. 1, 1. Next column, there are 3 ones in it. That's 1, 1. So 1, carry the 1, 1. And then this column has only 1, 1 in it, so lovely. And then the rest are zeros forevermore. And so that should be the answer. That should come out to be 450. That's a 2, 4, 8, 16, 32. There's a 64, 128, and a 256. So 256 plus 128 plus 64 plus 2, 14, 18, 19, 20. Oh, looking good. 7, 8, 9, and 6 is 15. And yes, it does come out to be 450. Okay, so that's multiplication. Ooh, fun one. Division. Binary division is done exactly the same as decimal division. You'll actually find that it's fairly easy, I hope. 9 divided by 3 is 3, and what would you do? You would say 3 goes into 9, 3 times 3 is 9, subtract, and you get a 0. So that's the same process that we're going to do. So we're going to see 3, which is, and I'm going to keep it 8 bits because we like to do that. 3, 4, 1, 2, that's a 3, and we want to divide it into 9, and 9 is 1, 2, 3, 4, 1, that's an 8, 0, 0, 1. So the way you approach this is, I'd say I'd look at these 2 bits right here, because these rest of these zeros don't matter, and don't let them fool you, because the rest of these bits don't matter. As a matter of fact, for purposes of this problem, I can erase the rest of those bits, because really I can put an infinity number of bits of zeros in front. It doesn't matter, I can put infinity number. And so I see that I have this 1, 1 right here, and I know 1, 1 cannot go into 0, 0, and it cannot go into 0, 0, 0, and it cannot go into 0, 0, 0, 0 evenly. And a matter of fact, 1, 1 cannot go into 1 evenly, or it can't go into 1 because 1, 1 is still bigger than 1. 1, 1 cannot go into, right now I'm at 1, 0, because this is 3 and that's a 2, so it can't do that. So the first place that it can go into is these 3 numbers right here, the 1, 0, 0, and it can go 1 time. Now you're only ever going to have a choice if it can either go 0 times, still goes 0, still goes 0, 1, 1 goes into 1, 0, 0 times, or it can go 1 time, and those are only ever your choices. So it went 1 time, 3 went into 4 1 time, because this is 1, 1 is 3 and 1, 0, 0 is a 4 basically. So it went in there 1 time, and now I multiply it out just like I would do in the decimal long division. So 1 times 1, 1 is that. You subtract, and so that'll be a 0, that'll be a 1, and that's a 1, 0, or a 2. So that will be 1 and 0 and 0. Can 3 go into 1? No. So bring down another 1. Can 1, 1 go into 1, 1? Yes, one time. And then remultiply this 1 times that, subtract, and you get 0. So that's how it works. Let's get progressively more complicated here, because it gets fun. So progressively more complicated. Next example is 15 goes into 135. So it goes exactly 9 times, and we will look at fractions here, and that will be 0. So 15 is 1, 1, 1, 1. And it is being divided into 1, 0, 0, 0, 0, 1, 1, 1. So 15 is being divided into 135. So as I said, you can ignore these first 4 leading zeros, and I'm going to go ahead and ignore them because they confuse the picture. And I'm going to tell you that almost every time, well, there's 4 digits here, you're going to need probably at least 5 digits over here. But does 1, 1, 1, 1 go into 1? No. Does 1, 1, 1, 1 go into 1, 0? No. Does 1, 1, 1, 1 go into 1, 0, 0? No. Does 1, 1, 1, 1 go into 1, 0, 0, 0? No, because 1, 1, 1, 1 is still bigger than 1, 0, 0, 0, so I get another 0 there. So the next one, does 1, 1, 1, 1 go into this 5-digit number? And the answer is yes, because the 5-digit number is bigger than a 4-digit number. And I can tell you right now, it will go 1 time. Your choices are 1s or 0s up in the top above the radical sign. So now I multiply it out, 1, 1, 1, 1, and subtract. So that becomes a 0, a 1, a 1, a 1, and a 1, 0. So 1, 0 minus 1, or in other words, 2 minus 1 is 1. That's a 0, that's a 0, and that's a 0. Now, does 1, 1, 1, 1 go into 1? No. Bring down a 1. Does it go there? 1, 1, 1, 1 go into 1, 1? No. Does it go into 1, 1, 1? No. Does it go into 1, 1, 1, 1? Yes, exactly 1 time. So then that 1 times that, 1, 1, 1, 1, subtract, and it's a 0. Yay! Okay, next one. Let's do one more. Let's make it one with a fractional answer, just to make it fun. Book doesn't have any ones with the fractional answer in it, I don't think, but we'll go ahead and do a fractional answer. Let's do 17 divided by 2. So 2 is 1, 0, and so 1, 0 divided in goes into 17 how many times? 17 is 16 plus 1. So 17 must be, that's a 16 plus 1. Let me write that better. That's 17, right? 16 plus 1 is 17. So 1, 0 doesn't go into 0, doesn't go into 0, 0, doesn't go into 0, 0, doesn't go into 1, but 1, 0 does go into 1, 0 one time. Multiply it out and we get 1. Oh, I thought I was going to get a 1, 0. So that's 0, subtracting those two. 1, 0 doesn't go into that, so I bring down another 0. That doesn't go in, that doesn't go in, and finally I get to bring down another 1. Whoops, I forgot these up here. So I get to bring down another 1. 1, 0 still doesn't go into there, So now I bring down another 0 right here past the decimal point. And does 1 0 go into 1 0? Yes, one time. And then I multiply those out, and my problem is done. So this says that my answer right here is 1, 2, 4, 8 with a remainder of 1 in base 2. So the remainder is 1 in base 2, but let's look at that remainder. What does that really mean? So 1, 0, 0, 0.1. So remember, this is the 2 to the 0th place, the 2 to the 1, the 2 to the 2, and 2 to the 3, which is 8. So there's where my 8 comes from, right there. And this place right here is 2 to the minus 1. And what's 2 to the minus 1? That's the same as 1/2, or 0.5. So when I convert, my answer is really 8.5. And surely 17 divided by 2 is 8.5. So that gives you an idea of how a decimal might be handled if you were going to do long division. So our subtraction that we're having to do up here, there is a better way, and it's called 2's complement. So I'm going to show you the 2's complement method coming next. In the 2's complement representation of a number, that's also like making the number be negative. You always, like here's my 8-bit number right here. The most significant bit is going to be the sign. And if this most significant bit, D7 in this case for an 8-bit number, or 1 byte, if that number is a 1, the number is going to be negative. If the most significant bit is a 0, then my number represents something positive. And that's also similar for a 16-bit number shown below. So the most significant bit is like the sign bit, saying whether you're a positive or negative number. So let me show you how it works for how you make a 2's complement number. So if I have the number 7, I'm just going to do it in 4 bits. Actually, I'll do it in 8 bits. Here's the number 7. This is a positive 7. If I want the number negative 7, I'm going to complement all the bits. So 1, 1, 1, 1, 1, 1, 1, 1. Nope. 0, 0, 0. Sorry, that's the complement. I'm going to complement and add 1 plus 1, and I get the number 1, 1, 1, 1, 1, 0, 0, 1. This number I claim is minus 7 in our 2's complement representation. And why do we want to have plus 7 and minus 7? Because recall that if I do the operation 5 minus 2, that's really equivalent to 5 plus negative 2. So this is how we're going to do subtraction in the binary world. We're going to only do additions, but we're going to make our numbers become negative. So let me do an example. What is 8 minus 7? So 8 minus 7 is 8 plus negative 7. So let's do it with our number that we just found out right here. So 8 is 1, 0, 0, 0, 0, 0, 0. That's the number 8, right? And I'm going to add negative 7 to it. And negative 7, I just found out, was 1, 1, 1, 1, 1, 0, 0, 1. So this is 8. And I'm going to add to it negative 7. And let's see what we get. We get 1, 0, 0. 1 plus 1 is 1, 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 0. And 1 plus 1 is 1, 0. But this bit right here, this fell out into the 9th place. It's not in the 8th place anymore. So my 8-bit answer is right here, and it is a plus 1. So it worked. 8 plus negative 7 is plus 1. a few more examples here. Let's do 21 minus 13. So that answer should be, whoops, 8, not 18. That answer should be 8. Positive 8 is the answer. So 21 is 1, 2, 3, 0. That should be 21. 16 plus 4 is 20, 21. Yes. And we got to find, we have to do, what we really have to do is 21 plus negative 13. And that's what the math that we really have to do. So we need to find out what negative 13 is. So to do that, we first find out what 13 is. So 13 is 1, 1, 0, 1. This is 13. This is the number plus 13. And we have to find the 2's complement of it. 2's complement of it. So, complement. That's what we have to do. So this is the number 13. So what we do to find negative 13 is complement it. Let's complement it and add 1. That's the routine. Complement it. 1, 1, 1, 1, 0, 0, 1, 0, and add 1. And we have 1, 1, 0, 0, 1, 1, 1, 1. So that should be minus 13. And since the most significant bit here is a 1, that means the sign is negative. This one up here, this number up here, 21, the most significant bit is a 0, so that means it's a positive number. So let's add positive 21 plus negative 13. 1, 1, 1, 1, 0, 0. That's negative 13. Add them up. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. 1 plus 0 is a 0. 1 plus 1 is 1, 0 again. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. And 1 plus 1 is 1, 0. Whoa! Whoa! I made a mistake. Because I can't add right here. 1 plus 0 is... I'm sure you guys caught that. You're like, no, Georgina didn't do it right. There it is. So, because 1 plus 0 here was a 1. And that answer is 8. This number right here is in the 9th position. It does turn out that that counts. Later on we'll learn that that's an indicator of overflow. But we won't worry about it just yet, because right now we have our answer right there is 8. Next example. Let's do an example where our answer comes out negative instead of positive to show you how that works. So 59 minus 96, which is the same as 59 plus negative 96. And if you do that math, the answer should be negative 37. So you take 96 minus 59 and change the sign, and the answer will be negative 37 in base 10. So now let's do it in binary. So 59 is 0, 0, 1, 1, 1, 0, 1, 1. That's 59. And we need 96 to be in negative 96. So first we have to find positive 96, and then we do the 2's complement of it. So positive 96. Oh, I think my brain is getting tired of doing these. Let's show you a shortcut. Here's my standard calculator. I'm in Windows 10 now, so it looks a little bit different than what I'm used to. But I can get the programmer calculator, and I can say that I'm in decimal 96, and it gives it to me here in binary. This Windows 10 calculator looks a little bit different, but let me put it over here. Decimal 96 is 96 equals 0 is 0, 1, 1, 0, 0, 0, 0, 0. That's plus 96. So I want negative 96, so I have to find the 2's complement of that. So the first thing I do is complement it. 1, 0, 0, 1, 1, 1, 1, 1, and add 1, because that's what 2's complement is. If I just complement it, by the way, it's called 1's complement, and it doesn't work as well as 2's complement. So anyway, so finish finding the 2's complement. 1 plus 1 is 1, 0. 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 1 plus 1 is 1, 0, 1, 0, 1. So that's negative 96, and it's that's correct. That's negative 96. And notice that my most significant bit is a 1, which indicates it's a negative number. So this is 59, and let's add to it negative 96, which is 1, 0, 1, 0, 0, 0, 0, 0. Add those two together. I get 1, 1, 0, 1, 1, 1, 0, 1. So this is my answer, and this most significant bit is a 1, which means it's a negative answer. Now, how do I convert that negative answer? I can't look at that and do my powers of 2 and come up with what that answer is. It doesn't work to do my powers of 2 thing right now. So what I have to do is 2's complement this answer back. So this is my answer. I know it's negative, so I'm going to keep track of it, but I'm going to take the 2's complement of this so that I can find what the positive equivalent is. So 2's complement of it. So first I'm going to complement 0, 0, 1, 0, 0, 1, 0, 0, and add 1. So this is the answer positive version of it, but I've kept track to the fact that I know that my answer is negative. So this is 1, 2, 4, 8, 16, 32. So 32, 36. So it does indeed equal 37. This is the number 37. But this is actually the answer right here in 2's complement form with the most significant bit indicating that I'm a negative number. And so my answer is negative 37, but if I wanted to find out what number that is, I have to re-2's complement it again to find out the positive equivalent. So yes, that's it.